Okay, so in our meeting on Tuesday, we started discussing dimensional analysis, although we didn't finish, but we discussed almost all the most important aspects of dimensional analysis. We discussed the application of dimensional analysis, and you've been given this document, which has example questions or a tutorial sheet or tutorial questions, which you're expected to solve, and it's containing questions on dimensional analysis, errors and uncertainty, and in general units and measurements. So question 1, 2, 3, up to 7, somewhere. I think we'll end up to 7. They are all looking at dimension analysis, basically the different aspects on which we can apply dimension analysis. We said we can apply dimension analysis in coming up with new formulas for newly developed physical quantities, also unit conversions from one unit to another, and also proving if a certain formula is dimensionally consistent or dimensionally upright or dimensionally correct. So that's basically what we'll be going to, or that we'll be doing in this tutorial. We can start with question 1 without wasting much time, which is involving a question and unit conversion. And it reads, the speed of light is about 3.0 times 10 to the power 8 meters per second. Express the speed of light in A, kilometers per hour, B, kilometer per minute, C, mile per hour. A, kilometer per hour, B, kilometer per minute, and C, mile per hour. Okay, so this is a very, very simple question. The only secret we're supposed to know here, or what we're supposed to understand before you start solving this question, is the conversion factors. So anyone who would love to help us, what do you think is a conversion factor, or what is a conversion factor by definition? What is a conversion factor? Anyone? Just a try. What do you think is a conversion factor? Okay, so label this one question 1. Well, 3 times 10 to the power 8 meters per second. And we're supposed to convert this into kilometers per hour in part A. What is the conversion factor? Okay. So we're going to, if we want to convert our meter per second into kilometer per hour, this is kilometer per hour actually, not kilometer per minute. This is kilometer per hour in A. If we want to convert our meter per second, our 3 times 10 to the power 8 meters per second into kilometers per hour, we're going to use a conversion factor of meter per second to kilometer per hour. So we're going to relate the same physical quantities to each other. In this case, we're going to relate the physical quantity for distance to distance and the physical quantity for time to time. So we have meter per second here, and we want to convert this meter per second into kilometer per hour. So what are we going to do? We're going to multiply this meter per second with a conversion factor that is directly equivalent to the kilometer per hour. And this is going to be like this. I'm going to have my 3.0 times 10 to the power 8 like this. This is what? This is meter per second. So this is per. It's the same as dividing. So I'm going to have my meter over per second like that. That means the second is a denominator. And I'm going to multiply this with a conversion factor. And that is 2 conversion factors because I'm dealing with 2 different physical quantities. I'm dealing with distance and the time at the same time. So I'm going to start with converting the distance and also convert the time. So here I'm going to put my dash there. Time is, or we can start with distance if we want. So we can see to say the meter here is a numerator, which means in our conversion factor, the meter is supposed to be a denominator. So how many meters are making up 1 kilometer? That is the conversion factor that we are going to use here. So we have 1 kilometer. We have 1 kilometer, which is equal to what? Which is equal to 1,000 meters. And this is going to make sure that this meter that we have as a numerator and this meter that we have as a denominator cancel out. That's the way we're supposed to arrange our conversion factors. Make sure the quantity or the unit of measurement that you want to get rid of should be on opposing sides. If it's a numerator in the original expression, it should be a denominator in your conversion factor. The goal at the end of the day is to make sure that you eliminate the unwanted unit of measurement. Okay, so from there, I'm also going to multiply this with the conversion factor for time. We have second here, and we want to convert our second into an hour. So what are we going to do? We're going to apply the conversion factor between an hour and a second. And we know to say 1 hour is equal to 3600 seconds. This should basically stick into or should be on your fingertips because these are some of the simplest questions you ever find. Okay, so I'll put my second as a numerator. Since it's a denominator here, it will be a numerator here. So I have my 3600 seconds like this, which is equal to 1 hour like this. So this second and that second are going to cancel out. That means I can now multiply what I'm remaining with, and I'm going to get the kilometer per hour that I'm looking for. So this is going to be equal to this. I'm going to say 3 times 10 to the power 8 multiplied by 1 kilometer multiplied by 3600, and I'll divide that by 1000 multiplied by 1 hour. And this is going to give me exactly 1.08 kilometers per hour. So 3 times 10 to the power 8 meters per second is equivalent to 1.08 kilometers per hour in this unit of measurement. And that is all on question A. Or yeah, question 1A. That is all about question 1A. We can look at question 1B, which is saying we should convert the speed of light into kilometers per minute. So we should convert this into kilometers per minute. As usual, what are we going to do? We're going to apply this same method. So I'm not going to spend a lot of time now explaining because we already know what is happening. So first things first, I'm going to say yes, I'll say my 3 times 10 to the power 8 meters there. The second is a denominator multiplied by, I'm now converting into kilometers per minute. So I'm going to have my conversion factor between the meter and the kilometer as usual. So I'm going to have 1000 meters over 1 kilometer as a numerator multiplied by the conversion factor between a minute and a second. So the second is going to be at the top. This is 60 seconds being equal to what? Being equal to 1 minute. Okay, so this is what I'm going to have. Then the meter and the meter are going to cancel out. The second and the second are going to cancel out. Then we can multiply the 3 times 10 to the power 8 by 1 kilometer by 60. Then we divide it by 1000 multiplied by 1 minute. And this is going to give us exactly B is going to give us 1.8 times 10 to the power 7 kilometers per minute. Okay. So after writing this power, I've just noticed to say in the answer for option A, we didn't include the power, but there was definitely a power that was given. So it's not 0.08 kilometers per hour, but it's 0.08 times 10 to the power 9 kilometers per hour, like this. Sorry for that inconvenience or for that mistake. Yes, but that is the answer for part A, and this is the answer for part B. Part C is saying we should convert this same speed of light into miles per hour. So what are we supposed to know? There's one thing that we're supposed to know here that is very important, and that is the conversion factor between a mile and a meter. Since we're trying to convert from a meter to a mile, we should know the conversion factor between these two. So 1 mile is equal to 1609 meters. This is given in if you've ever taken time to check most of the books that you used at secondary school, there was always this conversion factor, though you never really paid attention to it because it never mattered. So let's now convert 3 times 10 to the power 8 meters per second into miles per hour. So I'm going to multiply this by the conversion factor between a mile and a meter. So I'm going to have 1 mile. I'm going to have 1 mile there, which is equal to 1609 meters multiplied by the conversion factor for time, which is as usual, 3600 seconds over 1 hour. So the meter here and the meter there are going to cancel out. The second there and the second there are going to cancel out. We're remaining with the mile that we are looking for here and the hour that we're looking for there. So 3 times 10 to the power 8 multiplied by 1 mile multiplied by 3600 divided by 1609 multiplied by 1 hour. And part C is going to give us an answer, which is going to look like this. Let me just plug it into my calculator. Okay, so it's giving me 6.71. 6.71 times 10 to the power 8 miles per hour, like this. So this is the conversion of the speed of light to the different units of measurement that were required to put it in. So we've solved both A, B, and C. Unless anyone has a question up to this point. Anyone with a question? Any question? Okay, so if there's no question, we can move on to question 2, which is saying convert 15 newtons to the equivalent CGS system. Convert 15 newtons to the equivalent CGS system. Okay, so this is also a very, very simple question. This is question 2 now. We're converting 15 newtons to the CGS system. Okay, so what do they mean when they say CGS system? Anyone who can give it a try? What do they mean when they say CGS system? Any idea? What do you think is a CGS system? Okay, so in simple terms, these letters that we have here in this, I don't know if I can call it a mnemonic or word that we've been given, which is CGS. We have C for centimeter, C is for centimeter, G is for gram, and S is for second. So this one is for mass, gram. This one is second for time, and this one is a centimeter for length. So how can you explain what the CGS system is from what I've just mentioned? Collectively, we can call it the centimeter, gram, second system. So it's just a metric system, which is requiring you to use centimeter for length, gram for mass, and the second for time. As simple as that. That's what they mean when they say the CGS system or the equivalent in CGS system. So which means we're supposed to convert these 15 newtons into the CGS system, which means we're supposed to use the centimeter for length, supposed to use the gram for mass, and we're supposed to use the second for time. That's what they mean in this particular question. So how are we going to go about tackling this question? How are we going to convert 15 newtons into its uh, or its equivalent in the CGS system? Anyone who has an idea now? Okay, so one thing we're also supposed to know is that in the CGS system, 1 Newton is directly equivalent to another unit of measurement, which is a dyne. So what is the relationship between 1 Newton and a dyne in the CGS system? So 1 Newton is equal to 10 to the power 5 dynes. What does this mean? That means 1 Newton is equivalent to 10 to the power 5 dynes in the CGS system. So the dyne is the unit of measurement of newtons in the CGS system. So in this case, what we're going to do, we're going to convert this unit of measurement that we've been given from newtons into dynes. And from here, I'm sure everyone now can solve this particular question. Just kindly, quickly plug it into your calculators and tell me what you are going to get. 15 newtons when you convert it into dynes, given this conversion factor that we've written here, what is it going to be?
Um, 1.5 times 10 to the power 8.
Okay, very good. So we have 1.5. Well, let me say 1.5 times 10 to the power 6 dynes. That is the equivalent of 15 newtons when it comes to the CGS system. That means we're now using G, or we're using a gram for mass, we're using centimeter for length, and we're using S for second. I'm sure we all now understand about that, because we know to say units of force. When we say force, the SI unit for force is a Newton, but it's units in the CGS. We say it's a dyne, and the dyne is just containing these guys that we have, or that we've talked about here. That means it's using this, that, and that. And we know to say the units of measurements when it comes to force, it can also be expressed as mass multiplied by acceleration, like that. What does that mean? That means we have mass, which is kilograms, kg, multiplied by what? Multiplied by acceleration. And we said the acceleration is equal to what? Acceleration is equal to LT to the power minus 2. What does this mean? That means meters per second squared. So we are basically multiplying kg by meter over second squared, like this. So that means we have our kg here has been converted into grams, and our meter here has been converted into centimeters. Then we have the second for time. That means we have our 15 newtons converted into dynes, just like that. That's how I can simplify this question further, if at all there was anyone who had any queries anywhere. Is there any question on question 2? Any question?
Okay, no.
Okay, so if there's no question, we can move on to question 3. Question 3 is saying show that the following equations are dimensionally correct. Show that the following equations are dimensionally correct. So we have two equations. Equation A, which is saying final velocity is equal to initial velocity plus acceleration multiplied by time. Then we have our equation B, which is equal to stating P is equal to rho hg. P is equal to rho hg. So our goal or our job is to prove that these three equations are dimensionally correct. They are dimensionally consistent. And what do they mean when they say they are dimensionally correct? Anyone? That means the equations that we are having here must have the same dimensions. The right-hand side of your equation must have the same dimensions with the left-hand side of your equation. That means your equation is dimensionally correct. Hence, it's having uh, the same dimensions. Yes, I can put it in that manner. The same dimensions. Okay, so the final velocity, V, is equal to V initial plus AT as equation A, like that. And how we're going to prove that this equation is dimensionally correct? This is actually very, very simple. Why? It's because we have velocity here and acceleration and time. And you know to say velocity has dimensions of Lt to the power minus 1, acceleration has dimensions of Lt to the power minus 2, then time has the dimensions t, just like that. So we're going to use these dimensions to check dimensional correctness of our two formulas that we've been given. So we have uh, v here on the left-hand side, of which that is velocity. So I'm going to say my left-hand side is equal to Lt to the power minus 1, which will be equal to initial velocity. Initial velocity is also just velocity. So it's basically having the same dimensions as velocity. So I'm still having Lt to the power minus 1 plus we have acceleration multiplied by time. So we have Lt to the power minus 2 multiplied by t, like this. Okay, so we can now just solve this to show that the dimensions on the right-hand side are equal to the dimensions that we're having on the left-hand side. And how we're going to do that is actually very, very simple. We're going to multiply. So I'm having my left-hand side. Let me do this. My left-hand side is still equal to Lt to the power minus 1, which will be equal to Lt to the power minus 1 plus I'll multiply the time that I have here to Lt to the power minus 2. So what are we going to get if we multiply time and time here? So we know to say we're multiplying the same bases here, the same bases of t. This one has power 1, this one has power minus 2. And from algebra, we know to say if we're multiplying same bases with different powers, what do? We add the powers. So what are we going to have here? We're going to have t, or a, or rather, to the power t minus 2 plus 1, like this, which means we're going to end up with Lt to the power minus 1 being equal to Lt to the power minus 1 plus Lt to the power minus 1, like this. So we're adding this and this, which means I'm remaining with Lt to the power minus 1 being equal to 2 Lt to the power minus 1. And since this is dimensional analysis, remember, we explained to say dimensional analysis always ignores whole numbers. It doesn't deal with the whole numbers, but only dimensional quantities, because whole numbers are dimensionless. So they are basically ignored in dimension analysis. So this is the same thing that we're going to apply here. We're going to apply 2, or we're going to ignore 2 rather, since it's a whole number, and we're going to remain with what? We're going to remain with the left-hand side here, which is Lt to the power minus 1 being equal to the right-hand side after ignoring the 2, which will also be equal to Lt to the power minus 1. The left-hand side is equal to the right-hand side. Therefore, this formula is dimensionally correct. That is how we prove that this formula, final velocity is equal to initial velocity plus acceleration multiplied by time, is dimensionally correct. Unless anyone has a question. Unless anyone has a question. Okay, so if there's no question, let's move on to equation B. The equation B is stating P is equal to rho hg. P is equal to rho hg. Okay, so this is also another simple, interesting equation. We have P, which is equal to rho hg, like that. So we're supposed to understand all these physical quantities that we are that have been related, or which are in a relationship in this particular formula. So we have P here, which is standing for pressure. We have rho here, which is standing for density. We have h, which is standing for height or depth. And we have g, which is standing for acceleration due to gravity. So it doesn't matter whether you've added the gravity at the end, it still remains acceleration. So g is acceleration, h is for height or depth, rho is for density, and the p is for pressure. So we can write the dimensions of these guys individually before you apply them in this formula, because our goal here is also to check that this particular formula is dimensionally correct. So we have to make sure to say the dimensions that are on the left-hand side are correct or are similar to the dimensions that we're having at the or on the right-hand side of this same equation. So we have P, pressure, which represents force per unit area. So what dimension does it have? It has dimensions M, L to the power minus 1, T to the power minus 2. We have rho, which is density. Density is equal to what? Density is equal to mass over volume. We know to say mass has dimensions m, and volume is a cubic length. L squared is density, or mean L cubic L is density. So we're going to have length to the power 3. So it's the same thing that we're going to apply here, which means the dimensions for density are ml to the power minus 3, since we're talking about the mass over volume. What about the dimensions for h, height? This is basically distance. Since we're talking about depth or height, we're talking about distance. So the dimensions are just L. Then acceleration, we already know about this one. G is just equal to LT to the power minus 2. Okay, like this. So we're going to apply, we're going to plug these into our formula and check if our formula is dimensionally consistent. Okay, so I'm going to say my right-hand side, which is equal to ML to the power minus 1, T to the power minus 2 will be equal to, I'm now multiplying these three values that we have here. We have rho, which is ML to the power minus 3. We have height, which is depth, which is L. Then we have G, which is acceleration, which is L T to the power minus 2, like this. Okay, so from here, we can multiply the same bases on the left-hand side, or on the right-hand side, rather. So we have L here, and we also have L here, and we also have L there. So what are we going to do? If we are multiplying same bases, different powers, what do? You just add the powers of that particular base. I'm sure you already know about that one. And that's the same thing we're going to do here. So I'm having my m, L to the power minus 1, T to the power minus 2 being equal to, I have m, then I have L to the power minus 3, then I'm going to add plus 1, which is there, and the plus 1, which is there, since a single L is basically L to the power 1. So say plus 1 there, and another plus 1 there. Then you have T to the power minus 2. T to the power minus 2, like this. Okay. M L power minus 1, T to the power minus 2 being equal to, we can now simplify our right-hand side of the equation, and we're basically going to end up with m, then L, negative 3 plus 2, we're going to end up with the negative 1. So we're going to have L to the power minus 1, T to the power minus 2. And from here, ladies and gentlemen, you can confirm with me that the left-hand side of this particular equation is exactly similar as the right-hand side of this particular equation. Hence, the equation is dimensionally correct. And that is all on question 3. Is there anyone with a question on this one? Anyone with a question? If there's no question, we can move on to the next question, which is our question 4. And question 4 is saying, for two bodies having mass m and capital M with a distance r between their centers of mass, the equation for Newton's universal law of gravitation is F being equal to G, m, or two masses multiplied over r squared. In the above equation, F is the magnitude of the gravitational force and G is the proportionality factor called the gravitational constant. Find the dimensions of G. Find the dimensions of G. So they've told us to say F is equal to force, and they've told us to say R is the distance between the centers of these two objects, and the small m and the capital M are masses of these two guys. So what are we going to do? We're going to get this formula exactly as it is. So they've given us to say F is equal to G M, then capital M over R squared. So what are we looking for? We're looking for the dimensions of M. And you are looking for the dimensions of G. So what does that mean? That means we're going to make G the subject of the formula. And how am I going to do this? I'm going to say over 1, I cross multiply. I'm going to end up with G being equal to FR squared over M multiplied by the capital M, like this. So what are the dimensions of force and R? R is basically distance. So it has dimensions L. R is distance, so yeah, it has dimensions L. Then M is mass, so it has dimensions M, of course. Then force is the same as the mass multiplied by acceleration. So I have mass multiplied by LT to the power minus 2. These are the dimensions of the remaining physical quantities that we have in this particular formula. So we're going to use this to calculate or to find the dimensions of G. We'll plug them into this same formula. We're going to have G is equal to MLT to the power minus 2 multiplied by radius squared here. So I'm going to have my L, which is distance, squared. L squared over 2 masses multiplied there. So we're multiplying mass and mass like this. Okay, what are we going to end up with? We're going to end up with m to the power, or m to the power 1. Then we have L to the power 3, since we're adding 2 and 1 there. Then we have t to the power minus 2 over m squared like this. Okay, so from here, this m can cancel out with one of the m's here, which means we're having 1m as a denominator. So if we cancel out 1m from the numerator, which is on the numerator, with one of the m's that are on the denominator, we're going to remain with what? We're going to remain with 1m as a denominator. We're going to remain with 1m as a denominator, whilst we'll have no m on the numerator. That means these are the dimensions of what? Of G. These are the dimensions of the gravitational constant G. But how are we going to write them? We're going to say G has dimensions m to the power minus 1, since it's a denominator, L to the power 3, and T to the power minus 2. These are the dimensions of the gravitational constant G. Unless anyone has a question, ladies and gentlemen. Unless anyone has a question. Any question up to this point? Okay, so thank you very much. We've solved a lot of questions. Now it's your turn to just solve one question. Just one question. Let's move on to question 5. And I want you to help. I want any of you who has understood to help us with question 5. What is question 5? Okay, question 5 reads, in Van der Waals gas equation, uh, open bracket, P plus A over V squared, close, open, V minus B is equal to RT, where P is the pressure, V is the volume, and R is the gas constant, and T is the absolute temperature. Determine the dimensions of A and B. Determine the dimensions of A and B. So anyone to kindly lead us, what would you do if, or what would you do in this case? How are you going to solve for the dimensions of A and B in this particular scenario? Anyone to give it a try? Anyone, guys, just anyone, just to give it a try. There's no sin in trying. How would you solve question 5 in your own ways? I hope you're able to get what I'm saying, because it has started raining heavily here. So I can't even get what you are saying. But I hope you are able to get what I'm saying. Christopher, yes, sir, your mic is making noise. There's a lot of background noise in your surrounding.
So currently, I'm on Twitch, so somebody has.
Okay, so I'll just mute you in the meantime. Anyone, so no one wants to try question 5 out? This is a very simple question, by the way, yeah? Okay, so in question 5, we are also going to use the same principle that we've been using, the principle of dimensional homogeneity. So what does the principle of dimensional homogeneity state? One of the it states a lot of things, by the way, of which we'll be talking about them as we are going. But one of them that we're going to apply in this case in question 5 is that the only terms that can be added to or subtracted to each other should have the same dimensions. Only terms with the same dimensions can be added to or subtracted from each other. What does that mean? If you look at question 5, we're having our brackets here on the left-hand side. We have this bracket, which is containing p plus a over v squared. And we're also having this bracket, which is saying v minus b. And the principle of dimensional homogeneity states to us to say only terms with the same dimensions can be added to or subtracted from each other, which means if we're adding p to a over v squared, that means p and a over v squared must have the same dimensions. The same must apply to the second bracket where we're having v minus b. What does that mean? That also means v and b must have the same dimensions. So from here, that means we can just quickly grab this one and help us to calculate a, and also grab that one to help us calculate b. Since we're adding p to a over v squared here, that means these two guys should have the same dimensions. The same should apply to v and b. These guys are being subtracted from each other. That means they should have the same dimensions. As simple as that. So I'm going to get what I've said exactly and calculate for b, but also a. Okay, so this is question 5. And what do we have? We can start with either of these two guys. Let's start with the dimensions of b. So we've been told to say v minus b in the brackets here, and we're trying to calculate the dimensions of b. So since v or since b is being subtracted from v, of which v is volume, that means b should have the same dimensions as the volume. I hope you understand what I'm saying, huh? So since volume has dimensions of L to the power 3, that means these are the same dimensions that B should also have. Since B is being subtracted from volume, and volume has the dimensions L3. So what does that mean? That means the dimensions of B are equal to what? Are equal to L to the power 3, as the same as the dimensions of volume. Just like that. The same applies if we want to calculate the dimensions of A. We're going to use this same expression that we've been given to say P, which is pressure, plus A over V squared, like that. V is also equal to volume. We've been given this. So what does that mean? That means the term A over V squared is having the same dimensions as what? The same dimensions as P, which is equal to pressure. So what are the dimensions of pressure? Pressure has dimensions of force per unit area. Force per unit area. And we know the dimensions of area, and we also know the dimensions of force. So what are we going to do? We're just going to plug them in the way they are. We know to say force is equal to what? Force is equal to mass times acceleration, which means mass, m, multiplied by what? Multiplied by LT to the power minus 2, which is acceleration. Whilst area, we know to say to calculate area, what do you do? You say, what do you say? What do you say? You say L to the power 2. You say L squared, calculate area. L squared. So to basically be equal to length to the power squared, like this. So these are the dimensions of pressure. So I'm going to say A over V squared will be equal to the dimensions of P, which are equal to what? Who can summarize the final the final dimensions of pressure? I'm sure I can tell to say L there will cancel out with one of the L's that are on the denominator. Hence, we're going to remain with the one L on the denominator, and we'll remain with no L at all on the numerator. Therefore, we're going to have M L to the power minus 1, since it's a denominator, T to the power minus 2. So these are the dimensions of this pressure guy. So now that pressure is having these dimensions, or these are the same dimensions of this expression that we have here, what are we going to do? We already know the dimensions of V squared. So how are we going to calculate the dimensions of A from here? Anyone to finish this one? How can you finish this one now? Quickly, anyone to finish it. We have V squared. That means these are the dimensions of A over V squared. Now, what are the dimensions of A? That's a simple question. Since we know the dimensions of V squared. Guys, just say something. Whatever you say, it's correct. Okay, so we know to say volume has dimensions L to the power 3. And in this bracket, or in this expression, we can say to say it's squared. So that means it has a square outside there. So I'm going to say my A over L to the power 3 squared like that should be equal to M L to the power minus 1 T to the power minus 2, which is this guy that we have here. And from here now we can calculate the dimensions of A. So what are going to be the dimensions of A? Is going to have dimensions M L to the power 5 and T to the power minus 2. You're simply cross multiplying there. And there you have it. You have your dimensions for A and your dimensions for B, just like that. Is there anyone with a question? You have both your dimensions for A and your dimensions for B. Is there anyone with a question? Okay, if there's no question, let's look at the last one, or the last question for today, which is question 6. Let's look at question 6. So question 6 is saying a radioactive material decays according to the following equation. N is equal to N initial e to the power minus decay constant E. Okay, so this is the equation. I already know this equation, by the way, but I don't know how to mention these things too. So I have remaining activity is equal to initial number of atoms to the power, or multiplied by e to the power minus decay constant. This is the decay constant multiplied by T. So where N is the number of active nuclei and uh, at an instant T. And N initial is the initial number of active nuclei. Then we have the decay constant there. Find the dimensions of the decay constant. As simple as that. From this equation, find the dimensions of the decay constant. So what are we going to do here? Anyone who can give it a try? Anyone who can give it a try? We've been given this equation. Initial nuclear multiplied by e to the power minus decay constant at an instant t, like that. We're trying to find the dimensions of the decay constant. How are we going to do that? Anyone? How are we going to approach this particular question? And try. Which principle are we going to use and how are we going to approach this question? No one wants to give it any try? Okay, so we're also going to follow this principle of dimensional analysis, which states to say if your equation is dimensionally consistent, I've started feeling lazy, yeah? I don't know if people don't want to talk. I don't even know if you're understanding, because if I say any question, no question. Can you try this? Everyone is quiet. So I don't know how to check for facts, whether you've understood or not. So we're going to use a principle which is or which says for an equation that is supposed to be dimensionally consistent or dimensionally correct, whichever way you can put it. The argument of any exponential function must actually be dimensionless, which means the exponent for an equation to be dimensionally correct, the exponent should be dimensionless. So, for example, if you have such a number e to the power x like that, that means this exponent x must be dimensionless, like this. So now that we know this principle, what are we going to do in order for us to find the dimensions of the the decay constant? So we have this guy as an exponent. That is an exponent. And in our exponent, we have the decay constant itself, and we also have t, these two guys. So if we are saying our exponent must be dimensionless, what does that mean? We already know the dimensions for time. Say it's just t for time. Then what is going to be the dimensions for a decay constant? Anyone to give it a try now that we've broken it down and made it simple as such? Anyone? So I'm sure we understand to say if we say it's dimensionless, that means it should be equal to a whole number. Should be equal to one, for example. That means that is it, or that expression is dimensionless. If its dimensions are actually giving you a whole number, which is one, that means it is dimensionless. So in this case, how are we going to find the dimensions for the decay the decay constant if the dimensions of t, which is also part of the exponent, is equal to t? That's the question. Because this we're saying this should be dimensionless, right? Should be like this. What does that mean? That means we should say our decay constant multiplied by t should be equal to dimensionless, which is 1. We want to remain with our decay constant, so we're going to divide both sides by t, even this side by t. T and t will cancel out. That means we remain with our decay constant being equal to 1, which is the whole number, over time. What are the dimensions of time? It's the capital T that I've just written here. So we're going to have the dimensions for a decay constant as 1 over t, like this. Hence, we're going to remain with the dimensions of our decay constant as equal to what? As equal to t to the power minus 1, like that. That means the dimensions of our decay factor, or our decay constant rather, is equal to t to the power minus 1. Just like that, we are done with this particular question. Is there anyone with a question?